Hello. Today we are going to continue talking about hypothesis testing. In the previous section, we introduced the basics of hypothesis testing and kind of the overall structure of a test. Today we are going to specifically discuss the step-by-step procedure for conducting a hypothesis test for a population mean, assuming that sigma, the population standard deviation, is known. So we're going to focus on a specific method referred to as the p-value method. There's another method referred to as the critical value method that's sometimes used, less often though than the p-value method. So we focus on the p-value method in this class because that's kind of like the standard method that's typically used. And we'll talk a little bit about the relationship between hypothesis testing and confidence intervals. And we'll go back and talk a bit about errors, and and then wrap up. So let's dive in and go over the specifics of the p-value method for conducting a hypothesis test. So the p-value is what it is. It is the probability that a number drawn from a distribution of the sample mean would be as extreme or more extreme than an observed value of the sample mean. Okay, so when we are collecting data to conduct a hypothesis test for a mean, this involves collecting a sample from a population, computing a sample mean, and then we use that to find a probability. So basically the p-value tells us exactly how unusual the observed test statistic is. Okay? This will become a little bit more, as we dive into this, it'll become a little bit more apparent what we mean by this. But essentially, a smaller p-value is stronger evidence against the null hypothesis. Okay, so if your p-value is small, you are more likely to reject the null hypothesis. If your p-value is larger, you are less likely to reject the null hypothesis. So let's explore this in a bit more detail by introducing an example right here. Let's say that we have an online coaching program, and this program is supposed to increase the mean SAT math score to a value greater than 530. So we can set up a null and alternate hypothesis for this test. The null hypothesis is the assumption that nothing has changed, which means the mean would still be equal to 530. The alternate hypothesis is the assumption that the program is working the way it's supposed to, which means it will lead to a population mean that is greater than 530, right? So we set this up as a right-tailed test. Now, let's assume that 100 students are randomly chosen to participate in the program. Right? So we do a simple random sample of 100 students. They all participate in the program, and after the program, they all take the SAT, and we compute the mean of their SAT scores. And the sample mean is 562. And the question here is, suppose that the population standard deviation is known to be sigma equals 116. Does this provide strong evidence against the null hypothesis, right? The null hypothesis is the assumption that the population mean is equal to 530. And we obtained a sample mean of 562, right? So initially we might say, okay, well, it looks like the evidence supports the alternate hypothesis, right? Because the sample mean that we obtained is greater than 530, right? But remember, that is a sample mean. It's not a population mean. And when we looked at the central limit theorem back in chapter 7, we learned that the sample mean is a random variable, right? So if we collected another simple random sample of students and did the same thing, right, we might get a sample mean that's different from 562, right? So what we need to do is we need to say, okay, well, what is, basically we assume that the null hypothesis is true, right? And if the null hypothesis is true, that means the population mean is equal to 530. And we're going to use the central limit theorem and the sampling distribution for the sample mean, and we're basically going to ask the question, if my sampling distribution is centered over 530, what is the probability of getting a sample mean of 562? Is that probability really small? If that probability is really small, then we'd probably say, okay, well, the more likely scenario in that case would be that the sampling distribution is not centered over 530, but something bigger than 530. If that population is pretty large, or if that probability is pretty large, then we would be more likely to say the null hypothesis is true. Okay, so how do we do that, right? Again, we always assume we begin by assuming that the null hypothesis is true, right? And remember, if you go back to the central limit theorem, it states that the mean of the sampling distribution is equal to the mean of the population, right? So if we assume the null hypothesis is true, then we are assuming our sampling distribution is centered over 530. And furthermore, we can treat it as a normal distribution because the sample size is 100, which is greater than 30, right? So we are going to treat this as a normal distribution that has a mean of 530 and a standard deviation of sigma over the square root of n, which would be 116 over the square root of 100, which equals 11.6, right? So at this point, we're just assuming the null hypothesis to be true and looking at the sampling distribution under that assumption. Now, let's compute the z-score. Now, in the language of hypothesis testing, we use kind of some specific terminology, and the z-score is referred to as the test statistic. That's a terminology that's kind of specific to hypothesis testing. But if we compute the z-score using the z-score formula, x bar minus mu divided by sigma over the square root of n, right? That's the z-score formula for the sampling distribution. The sample mean was 562, and because we are assuming that the null hypothesis is true, then we will plug in 530 for mu, and then divide by sigma over the square root of n, and the result is 2.76. Now, if you look at that, 2.76, that means it's 2.76 standard deviations above the mean, right? So the sample mean of 562 is 2.76 standard deviations above the mean. And again, we're assuming the mean here is 530, right? That is pretty far out in the tail of the distribution. Remember that normal distributions follow the empirical rule, and one of the statements that the empirical rule makes is that you would expect 95% of your data values to fall within 3 standard deviations of the mean. 2.76 is getting pretty close to 3, right? It's pretty unusual to have data values that far out, right? We could probably reasonably say that 90% of your data values or more will have z-scores less than 2.76, right? So if the sampling distribution is actually centered over 530, the likelihood or the probability of getting a sample mean of 562 is actually quite small. Like, it could happen, but you'd be much more likely to get sample means that are Sorry about that. Let this go away. So you'd be much more likely to get sample means that are a little closer into the mean, right? Sample means that are closer into the peak of the distribution, right? So what we would say is that the evidence here suggests that the null hypothesis is probably not true, right? Because the probability of the sample mean being 562 is quite small, if the mean of the distribution is 530, a more likely real-world scenario is that my distribution is centered over a number that is bigger than 530, right? So we kind of go with the more likely scenario in this case, right? And we'd say probably the value of mu is actually bigger than 530, right? Which suggests that the alternate hypothesis is true. If I wanted to figure out exactly what the probability is of getting a sample mean of 562, assuming the population mean is 530, then what I'll do is I will just find the area under the normal curve to the right of z equals 2.76. I can find that using the chart. I can find that using my TI-84 calculator, using one of the methods we've already covered. Either way, if you look up that area, it's going to be 0.0029. Again, that's a very small area, right? So we could say that if my sampling distribution, which represents the distribution of all possible sample means, if it is centered over 530, the probability of getting one specific sample mean of 562 is 0.0029. That's an extremely small probability, very unlikely. So the more likely scenario is that the population mean is actually bigger than 530, right? So because this area is so small, it suggests that the null hypothesis should be rejected. This area, we refer to that as the p-value. Again, that is a specific terminology that we use for hypothesis testing, right? But it refers to a specific area under a normal curve. And this also makes it a little bit more apparent why we use language like right-tail test or left-tail test, right? This was set up as a right-tail test because the alternate hypothesis used a greater than symbol. And the p-value then is the area in the right tail of the normal curve, right? If we were doing a left-tail test, then the p-value would be the area to the left of the z-score, or the area to the left of the test statistic. So that with the p-value method, what you do is you look at the sampling distribution under the assumption that the null hypothesis is true. And then you find this p-value, and if that p-value is very small, then we would be likely to reject the null hypothesis. If the p-value is fairly large, we would be more likely to not reject the null hypothesis, right? So it's the p-value that we use the p-value to make the final decision. So then that kind of begs the question, well, how small does it need to be before we choose to reject it, right? What's the cutoff? And that is a very good question. And what we typically do is we kind of choose that cutoff value before we even conduct the test. We basically choose a number, and we say if the p-value is less than or equal to this number, I'm going to reject the null hypothesis, right? We choose that number before we even conduct the test. We call that number the significance level, or the level of significance. And it's fairly common to use the Greek letter alpha to represent that. It's a number between 0 and 1, but it's always going to be much closer to the 0 side of that. Common values for alpha are things like 0.05 or 0.01. And then, so that is always chosen at the beginning. And then we find the p-value, and if the p-value is less than or equal to alpha, we will reject the null hypothesis. If the p-value is greater than alpha, we will not reject the null hypothesis. Okay? If the p-value is less than or equal to alpha, we say that the null hypothesis is rejected at the alpha level, or that the result is statistically significant at the alpha level. Okay, so let's suppose we conduct a hypothesis test and we found a p-value that was 0.0122. Do you reject the null hypothesis at the 0.05 level? Yes, right, because the p-value is less than 0.05. But would you reject the null hypothesis at the 0.01 level? The answer is no, right, because the p-value is greater than 0.01, right? So the choice of alpha is the deciding factor as far as whether the null hypothesis is rejected or not. In the homework problems and on the test problems you'll be doing, the value of alpha will be chosen for you, and your job will be to find the p-value and then compare it to that chosen value of alpha. So let's go and take a look at an example. So let's say the mean height of adult men in the United States is 69.7 inches, with a standard deviation of 3 inches. A sociologist believes that taller men may be more likely to be promoted to positions of leadership. So the mean height mu of male business executives may be greater than the mean height of the entire male population. A simple random sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of male executive heights is sigma equals 3 inches. Can we conclude that male business executives are taller on the average than the general male population at the 0.05 level? Okay? So we're going to conduct a hypothesis test here. The first step, we should always check our assumptions. The assumptions are that the sample needs to be a simple random sample, and the sample size needs to be large. This will only work if we can treat the sampling distribution as a normal distribution, right? In this case, it says we have a simple random sample of 100, right? So both of those conditions are met. So the assumptions are satisfied. Now we can establish our hypotheses. The null hypothesis is the assumption that there is no change or no difference. And that would be the assumption that the mean height of men in general and the mean height of male business executives are the same, right? So the null hypothesis would be the assumption that mu equals 69.7, where mu is the population mean height of male business executives. The alternate hypothesis is the assumption that male business executives are on average taller than men of the general population. So because it says taller, it suggests an increase, so we'll set this up as a right tail test. Mu is greater than 69.7. The next step in my testing procedure is to consider the sampling distribution, and we will assume for the time being that the null hypothesis is true. So that means we will assume that my sampling distribution is a normal distribution that is centered over 69.7. With that assumption, we will compute the test statistic, which is the z-score. And the sample mean value is given as 69.9. For the population mean, we'll plug in 69.7, and we'll divide by the standard error, or standard deviation of the sampling distribution, which is sigma over the square root of n, or 3 over the square root of 100. which is equal to 0.3. When we do that calculation, we get a z-score of 0.67. And since this is a right-tailed test, the p-value will be the area to the right of z equals 0.67, which we can find using the table or the calculator, right? One of those two methods. But if we do that, we should find the area to the right of z equals 0.67 to be 0.2514. Okay? And then the last thing is to take that p-value and to compare it to our value of alpha. Alpha was given in the problem as 0.05. And my p-value in this case is quite a bit larger than 0.05. So since the p-value is greater than 0.05, we will not reject the null hypothesis, right? Now again, it's important to point out that this does not necessarily mean that the null hypothesis is true, right? It's simply saying that we don't have enough evidence to reject it, right? So we'll conclude by saying there is not enough evidence to conclude that male executives have a greater mean height than adult males in general. The mean height of male executives may be the same as the mean height of adult males in general, and that will be our conclusion. So that's the main process for conducting a test, right? You will set up your hypotheses, consider your sampling distribution under the assumption that the null hypothesis is true, compute a test statistic, which is the z-score in this case, and then use the test statistic to find a p-value, which will be the area under the curve to the right or to the left of your test statistic. Let's do another example. At a large company, the attitudes of workers are regularly measured with a standardized test. The scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their job. The mean score over all of the company's employees was 74, with a standard deviation of sigma equals 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers could spend 1 day per week working from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see whether their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume the standard deviation is still sigma equals 8. Can we conclude that the mean level of satisfaction is different since the policy change at the 0.05 level? First, check our assumptions. The sample is a simple random sample. The sample size is 76, which is greater than 30, so our assumptions are satisfied, and we can treat the sampling distribution as a normal distribution. Next step will be to establish our hypotheses. The null hypothesis is the assumption that nothing has changed, right? If nothing has changed, then the mean score will still be equal to 74, what it was before, right? The alternate hypothesis will set this one up as a two-tailed test using just the not equal to symbol. The reason for that is because the way the question is phrased, it just says different, right? It is not, the word there does not suggest an increase or a decrease, right? So it just says different. It doesn't have a descriptive term about how that is different. So when that's the case, we set it up with just the not equal to symbol, and that is a two-tailed test. Next step is to consider the sampling distribution under the assumption that the null hypothesis is true, right? If the null hypothesis is true, then the sampling distribution will be a normal distribution that is centered over 74, and the standard deviation will be sigma over the square root of n, which is 8 over the square root of 80, which is 0.8944. The next step is to compute the test statistic, or the z-score. Again, assuming that the value of mu is equal to 74. So we got 76 minus 74 divided by sigma over the square root of n. That gives me a z value of 2.24. Now, with a two-tailed test like this one, the p-value will be not just the area to the right of 2.24, but also the area to the left of negative 2.24. It'll be the sum of the area in both tails. Both areas will be the same because of the symmetry of the curve. So the easiest way to do it would be to just find one of the areas from the table, right? Maybe find the area to the right of positive 2.24, and then just take that area and multiply it by 2. Okay? So that's the extra step that you'll have to take with the two-tailed test. It's double the area that you find from the chart or from your calculator. So the area of one of the tails is 0.0125. So both tails together gives me a p-value of 0.025. Then we compare that to my value of alpha, which was 0.05. P-value is definitely smaller than 0.05, so that means we will reject the null hypothesis at the 0.05 level, and we will conclude that the mean score among employees has changed since the adoption of telecommuting. Okay, let's just go over now how we could do this with the TI-84. The command you will want to use on your TI-84 is called the z-test command, and you'll find it in the tests menu. Press the stat button, highlight the tests menu. It's the same menu that has all the functions we've used for confidence intervals. Z-test is the one at the very top. And your input option can be either data or stats. Stats is the option that you would choose if the summary statistics like the sample mean, standard deviation are given. So like with the two examples that we just looked at, stats would be the correct input method because sample means and things were provided for us. If all you're given is the raw sample data, then you would enter your data into the list editor, and then you would choose data as your input option. Okay. So let's revisit this example about the workers and the telecommuting policy. This time we will do it using the TI-84 calculator. Assumptions are checked, hypotheses are stated, right? So once you open up the z-test and you want to select stats as the input option, and you'll get an input screen that looks like this. For mu0, that's the null hypothesis, you'll put in 74, right? Because the null hypothesis is the assumption that mu equals 74. Sigma is given as 8, type that in. Sample mean is given as 76, type that in here. 80 is the sample size, so that's what you'll put in front of the n. And then down here you can choose two-tailed, left-tailed, right-tailed, right? So those are your options. This one is a two-tailed test. You select that. Ignore the color. I think most calculators don't even give that option. And then just go down here to calculate, press enter, and it will give you this readout. And it gives you the z-value and the p-value. So this the p-value is circled here because that's really the most important number that you'll want to look at, because that's the number that you'll then compare to your value of alpha to reject the null hypothesis, right? So z-test is what you'll use to do hypothesis testing of the type that we're looking at in this section. Okay, so what we've done now is we've actually looked at two different ways of kind of analyzing a population. One way is to create a confidence interval. Another way is to conduct a hypothesis test. The purpose of a confidence interval is to estimate the value of a population parameter. The purpose of a hypothesis test is to make a decision about a population parameter, right? So there are two different approaches. And oftentimes you could choose one or both, either or both methods to analyze a population. And if it's done right, the two methods should give results that are consistent with each other, right? For example, in the previous example, we rejected the null hypothesis. And the null hypothesis was a statement that mu equals 74. And we rejected it at the 0.05 level of significance. In doing so, we are saying that 74 is not a plausible value for mu, for the population mean, right? Because we rejected it, it's not a plausible value. Another way to express information about the population mean is through a confidence interval. If we construct a 95% confidence interval for mu about the attitude of workers using the methods that we went over in Chapter 8, we would find the interval to be this. It would be an interval that says that mu, the population mean, falls somewhere between 74.247 and 77.753 with 95% confidence, right? And we note that this interval does not contain the null hypothesis value of 74, right? 74 falls completely outside this interval. So the confidence interval mu, we would say, contains all of the plausible values for mu. And because 74 is not in the interval, then again, this result tells us that 74 is not a plausible value for the population mean, right? So what this does is it just highlights, yes, these are two different ways of analyzing a population, but we can, the results are consistent with each other because both methods tell us that 74 is not a plausible value for the population mean. Okay, let's revisit the idea of errors, which we discussed a little bit in the previous section. And just to review, a type 1 error occurs if we reject the null hypothesis when it is true. A type 2 error occurs if we do not reject the null hypothesis when it is false. Now, obviously, making errors is not desirable, right? We don't like to commit errors, but there's no way to completely eliminate the possibility of making an error. However, we can control the probability of making an error. That's something that we do have control over. Turns out that the probability of a type 1 error is actually equal to the significance level, denoted by alpha, right? So, if we perform a test at a significance level of 0.05, we can interpret that as saying that the probability of making a type 1 error is 0.05. So the question here is, obviously making an error is always bad, right? And since we have control over the value of alpha, we can choose any number we want to for that. Why don't we always choose a very small value for alpha? Why would we choose 0.05 instead of, say, 0.01 and decrease the probability of making a type 1 error even more? Well, the reason for that is that when we choose a smaller value for alpha, then the probability of making a type 2 error actually increases, and that's typically represented using the Greek letter beta. And so the probabilities of making these two types of errors are inversely correlated. If you decrease one, you increase the other. Most statisticians would say that the consequences of making a type 1 error are a little higher than a type 2, which is why more control is placed over that one. And you can decrease the probability of making both types of errors by increasing the sample size, but there's, of course, limits to that as well. But that's why, this is similar to our discussion confidence intervals about why you might choose like 95% confidence, right? Because if you increase your confidence, you also increase your margin of error. It's a similar sort of situation here, right? If you decrease the probability of a type 1 error, you actually increase the probability of a type 2 error. So oftentimes a value of alpha of about 0.05 is chosen as a good value, right? Because it's still small, but it kind of represents a healthy balance, if that makes sense. And then finally, when you conclude a hypothesis test, it's a good idea to not just state whether you rejected or not rejected the null hypothesis, but also explicitly state what your p-value is, right? And the reason for this is because there's some level of subjectivity as to what the value of alpha, right? If you choose alpha to be 0.05, somebody else might disagree with that and say the value of alpha should be something else, right? And that's important, right? So for example, at the 0.05 significance level, there's a huge difference between a p-value of 0.049 and a p-value of 0.0001, but technically both of those p-values would result in the same decision being made at the 0.05 level, right? Because both of those p-values are smaller than 0.05. But because not everyone may agree with your choice of alpha, by reporting the p-value, that allows people to decide for themselves at what level they would reject the null hypothesis. So that's just considered good practice to report your p-value and then report your decision. Report both of those things. So that wraps up this section, right? We've gone over the basics of the p-value and how to perform hypothesis tests about mu when sigma is known with the p-value method. We've looked at the relationship between hypothesis tests and confidence intervals, the relationship between alpha and the probability of error, and the good practice of reporting the p-value. Now in the next section, we will explore how to conduct a hypothesis test to make a decision about mu if sigma is not known, right? So we have kind of the same problem we had with confidence intervals in that sigma is usually not a known value. And once again, we'll have to revisit the student's t-distribution in that section and use that distribution to find our p-values. So we'll revisit that and go over how to tweak this method a little bit to still be able to conduct the test if sigma is not known. But that's it for this section, so thank you.